So, thanks for the introduction. My name is Delyan. I'm a last year PhD student at the University of Bristol School of Mathematics. I have a couple of months left to finish my PhD, and before that I did applied math masters in Sofia University in Bulgaria. So I'm going to talk to you about white noise testing using wavelets. So white noise is something that I try to explain to you. Testing, by testing I mean statistical testing. And wavelets is kind of the mathematical basis that I use to do this. So mathematically we'll start with a dry definition. A stationary, independent, identically distributed stochastic process over discrete time would be white noise if its power spectrum is uniformly distributed over all frequencies. Which means that if you observe a process, say, every month, and you have some seasonal effects, say, every third month you get a bonus from your employer, then you have a frequency of 1/4 for this bonus. So, on the one hand, you have time domain data, every point each time. This could be mathematically transformed to analyze the frequency of this. So this also means that the process must not be correlated at any point. And this means that the value today should not be very close to the value yesterday or the value 2 days ago, so on and so forth. Just colloquially, if you were a researcher in applied field and you wanted to see your data, there will be white noise if there is just no visible structure in there, and they have constant average value, and their variance doesn't change over time. Why is important? Well, in medicine, it's used heavily for hearing-related problems, attention deficit syndrome, and sleep disorder. Just to give you a hint, if you go out in the nature and you lie down next to a river, and then you listen to the sound of the river, this is what white noise is, as a sound. In statistics, in general, whenever you do regression or any model, the model wants to be, you want to decompose the model into something which is called the signal. This might be a mathematical function, might be physical approximation, you name it. And the noise is assumed to be white, and even more, sometimes people want the noise even to have a normal distribution, especially in the least regression cases. So how does it look like on a grayscale? This is how it looks like. When you were a little kid and if you have an old TV and there was no television, this is what you are going to see as well. So how do we measure the spectrum? Well, we have mathematical theory. There is something called the Fourier transform, which will transfer your data from the time domain to the frequency domain. However, we need to write down integrals. However, in real life, we have data. Data are discrete, The world is continuous, but we live discretely. So there was a famous mathematician who devised a way to do this transform. His name was John Tukey, and moreover, if you have a t data points, it will take only t log t time to compute your Fourier transform. This is what you get. So a part of the constant, xt is just your data points. This is the complex exponential or sines or cosines. Essentially everything is decomposed as a superposition of sine and cosine functions. And we have particular Fourier frequencies which start from 1 to the half of the data, which means that you get yearly data for maximum frequency for 6 months, which is half of the data. So if you have white noise, the discerning property is that the spectral density of the white noise would be just a flat line. No frequency would be dominating over other frequencies. It's called white noise because this is analogous to the spectrum of white light. Of course, we know that light has different colors from Newton 300 years ago in Cambridge. And this is because the amount of energy distributed to every different color is the same. So altogether when the energy is the same, you have white light, so that's how you have white noise. However, the periodogram is a discrete real-world approximation, so it will suffer from measurement error, no name it. It's just mathematical approximation. However, if you assume that you have white noise and want to check if your process is white noise, then it has a famous probability distribution under certain conditions which are excluded from this talk. So if we want to test this hypothesis of white noise, then we need somehow to factor in the equation. So to do that, I'm going to use Wavelets. This is a relatively new mathematical tool. By new in mathematics, you mean something that is 20 or 30 years old in popularity. And a very simple example for wavelets is just a function which has a process from which to generate another function. And in the very simple case, it would be 1 if x is from 0 to a half, and minus 1 if x is from, this should be 1 half to 1. Then the discrete wavelet transform, at the very simplest case, would be just having your data, then take every even point and subtract the point before which precedes it. So you'll have a series, if you have, say, 10 data points, then on the fine scale you'll have 5 wavelet coefficients, then you'll have, if you have 12, you'll have 6, then you'll have 3, and so on and so forth. And it's usually the best way to work with the 2 to the power something on your data. So, in order to test the constancy, this means that all the coefficients must be 0. Because we analyzed all the frequencies, so if 2 frequencies have the same energy, then the difference must be 0, or a number which is probabilistically 0. Because this is just additions and subtractions, we could do a mathematical formula for this. Then we have sums of differences for these exponential random variables. They have, this special case of a gamma distribution. Then we have difference of 2 gamma functions, and then we have this which looks a bit ugly. However, this bit on the right is the Bessel function of the second kind, which physicists, I guess, they know. And this is what actually explains to you the circular symmetry, because the periodogram ordinates might be looked also as complex numbers, and that's a topic for another topic. So when you have a test statistic, you have a distribution, you want to understand by its multi-distribution function what's the probability left in the tail, so that you can decide whether or not the test statistic that you have observed, say frequency a half is bigger than frequency a third, for example. However, because you start with T data points and then you have T wavelets coefficients, then you have to do something which is called Bonferroni correction, which actually translates to the fact that if you have a risk level of 5%, however, if we're going to do 10 tests, then you have to drop the risk level to 0.5%, so that the overall risk stays at 5%. And again, because we have many of them, then we need to have a single measure for whether or not our test is successful, then you need to take the mean, which makes this test very conservative. We have very good results for particular classic models. We developed theoretical power function, which is the essence of what a researcher might want from a statistical test. If you're a researcher in applied field, you might ask the question, how many observations do I need so that I can detect certain effect, or so that I know that my power is 80, 90, or 100%. And we have a package for the R programming for statistical programming language called H-double-double-line test. You can check it if you're interested. And just to show you the calculation for statistical power, this is a very simple model. The value today equals the value yesterday times some number plus some random white noise. Obviously, when this number is 0, this will be white noise. If this number has a value, this will be an autoregressive process. Then we have different tests here which we try to do, but what is essentially for a researcher to notice is that when the number of observations grows large, then most of the tests have a statistical power of 100%. This is very important mathematically because this means that your statistical test has asymptotical consistency, which means that the more data you get, the more sure you are that you're going to detect the effect that you were looking for in the first place. So some practical example, 2 weeks ago I read in the Telegraph that the FTSE 100, which is the Financial Times Stock Exchange Index, has hit a new high, and it has been the largest, price of the index since the dot-com bubble in 2000. So I decided to take just, small number of data points, 138 data points, which translates from May 2000 to September 2002. I decided to take every Monday. Just why those data? Because there is something called the efficient market hypothesis in financial markets, which means that you can't predict the markets. You can predict only relations between different stocks or stuff like that. However, the markets are just white noise, or the big father of white noise, which is the random walk. Obviously, those data have general downward trend. You see the big spike here. This is the Monday after September the 11th, 2001. That's in the US, so that's why the index dropped a lot. Then, for Financial Times series, people do transformations which are deterministic. For example, you may take the natural logarithm of your data and then take the difference of the data. So the value today, you subtract the value yesterday, and so on and so forth. Actually, mathematically, this means that this is the logarithm of the ratio of today's return over yesterday's return. Because you want to exclude the variance, you want just to see whether there is a growth or decline, and you want to subtract or contract the variance that you get. And if I take those data and I just take their logarithms, then I do the subtraction for a different subtraction, this is what I get. This is something which looks really like white noise, but I want to be able to check it and do this formally. How I'm going to do it formally? Well, there are different tests. The first 3 are ours, the other 2 are state-of-the-art in statistics. People who are interested in statistics know them. You don't need to follow with their names if you're not interested. This is what is called a p-value. In general, we look for this to be greater than our prescribed rate of error, which would be 5% or 0.05. Given that all of those are greater, we might infer that the previous data are white noise. And this is also plotting the uniformized cumulative sum of the parallelogram ordinates or the frequency values against the ideal value, and we see that there is not much deviation. So after the log returns transformation, we have white noise, so the efficient market hypothesis works for FTSE 100. That's it. Some references.
Okay, thank you very much. We'll now take some questions.
Can you use that to become a millionaire?
Yeah. If you find, some positive or negative correlation in some index, a financial index, or a combination of financial indices, and you don't tell anyone about it, and then you design your own trading strategy, then, because essentially, people make money on the market, and even if you take more of those data and you try to different resolutions, you see that, in the old days, when resolution was not great, you didn't have, data every 30 seconds or something, people were able to make, not that amount of money. But once, after the 1980s, they plugged a lot of computers in there and then made really high frequency trading, then, people started making quite a lot of money, and obviously some other countries or banks lost quite a lot of money.
So how many variables can you have in such a system?
How many?
Variables, or let's say stock prices of different
Well,
stocks?
you might have heard, there has been this experiment with some stock prices people that, like, a few of the best researchers designed a special portfolio, and then another researcher designed a random portfolio, and then at the end, all the returns were white noise. So essentially, this means that financial markets are a gamble. So, yeah, in a gamble, if you enter in a good position, then you can win. However, the casino wins always in the long term. This is what.
So it's best to own the casino rather than...
Yes, exactly. Rather than be a mere player.
That's very important.
Just one more question. How fast is the wavelet method compared to the horizontal one? Can you compare execution?
Okay, yeah, so the wavelet methods, there have been some very smart French people who can compute the discrete wavelet transform in linear time. So it's even faster than the discrete Fourier transform. But obviously first we do the discrete Fourier transform so that we get the estimation of the spectrum, and then on the discrete Fourier transform we execute the wavelet transform, and then we go out distribution and stuff.
So it can be used at real time.
It can be used. If you have obviously sequential data, you might change your matrix and just the upper triangle apart and the increments.
Do you know whether someone is trying to use these wavelets for finding patterns? Or?
Well, yeah, I know some people because part of my project is related with EDF, which is the French electricity company, which have a market here. So they have curves. So you have every half hour you record the load on the electricity grid. So for every day you have 48 values, which make them a curve, right? However, if I give you two curves and ask you, are they similar? And I ask all the people in this room, everyone can say a different answer. Because even just if I give you an interval and give you a pen, you can draw an infinite number of curves, because mathematically this is the square integral of Hilbert space, blah, blah, blah. However, the point is you can use wavelets to define a score for each curve, and define similarity between curves or their derivatives or some other tricks, because we're not interested in the mere distance between curves, but rather what does the shape of the curve tell you, and it grows or it decays. So choose for what is called clustering and segmentation. Volatility clustering, you have volatility curves for financials, for energy, because essentially, mathematically, the framework is the same.
In the function which you showed, it has just three values. Are you usually using these kind of functions, or I think it was an example of wavelets? With values 0, 1, and -1.
Okay, so this was just the first scale of the wavelet, because essentially a wavelet this was a discrete wavelet, so it was just the value 1. However, if you go deep in wavelets, wavelets are themselves little waves. So you have wavelet which looks like a Mexican hat. You have wavelet, if you take the Fourier transform of a wavelet, you get another wavelet, which however is not in the time domain, and it's in the frequency domain, and then you get all shapes and sizes. Because essentially there are infinite number of wavelets existing on the Earth. However, you have to be a French and very smart mathematician in order to design the process which will generate wavelets. But just count down, there are so many of them already generated that we can use them. So we don't need to generate new ones. We just need to explore better ways to use them.
I have a final question. So you mentioned that you've got a package on R.
Yes.
So a lot of us use R every day. So I was wondering if I enter your package and I decide I want to use it, what do I need? What would that package provide me with? What can I expect it to do? It will generate perfect white noise for me, or?
Yeah, you can do simulations. We have a special function which can give you theoretical power, because what I mentioned probably was misaligned is that our test here, one of our tests, there are actually 3 tests, but it's in the paper, it's open source, you can check it. So for a given automatic hypothesis, you suspect that your data might not be white noise, but some process, say of the class of all progressive moving average processes, then you can generate the theoretical power from the real spectrum, and you can evaluate, the weather conditions of the real spectrum and do it on the data. It will also give you another white noise test of Bartlett, Youngbox, so much are not that popular like Bartlett, and it's open source. Anyone can use it.
Yeah. Okay, any further questions? All right, thank you.